Yeah, and of course, instead of just applying some distance measure, similarity measure on the raw time series or on the preprocessed time series, we of course can also extract features from time series. Sometimes that's quite meaningful, and you can do, or in the literature, there are two general ways to do feature extraction from time series for two different purposes, actually. The first one is to reduce long time series to a more compact representation so that computations are more efficient and stuff like that. Think about the curse of dimensionality. Long time series, Euclidean distance, curse of dimensionality. Okay. And the second purpose is to really extract features out of these time series that somehow reflect some specific semantics. Yeah, application dependent semantics. And we have some examples for both of them. The first purpose, reducing the complexity of the time series, is probably more prevalent in real applications, but the other one, extracting some semantic features out of that, is of course also prevalent in applications, and we will see some examples here. So, this is what I just said. Instead of directly working with the raw data or the preprocessed data, we can extract features, and one of the two methods is to have a more compact representation, and there are a lot of things that you can use for getting better or more compact representations, which is closely related to dimensionality reduction, feature selection. And the second one is to extract semantic features specific to some given application. And we'll start with the first one here. And this is just an overview. Again, a lot of material here taken from Eman, from Eman's tutorial on time series analysis. And once again, the aim of this first class of methods is to find a more compact representation of the original time series without losing, of course, too much information. So that is perfectly matching the ideas of dimensionality reduction here. And the most general approach here, most of these approaches, specific approaches follow here, is to represent the time series by a combination of base functions. And all these methods, different methods here that you see, it's just a sample. There are a lot of other things going on or things existing. Those try to represent the time series just by different base functions. So Fourier transformation, for example, it's about sinus and cosine, sine and cosine base functions. Wavelet, not dynamic warping time, dynamic discrete wavelet transformation here. It's about wavelet functions. Singular value decomposition can be done with these. Then we're talking about eigen curves, and so on and so on and so on. So we'll see that now in the following. So the first one here is a DFT, discrete Fourier transformation. So the base functions are parametric functions like sinus and cosine, with different frequency. So here's an example. This is the original time series, and if we take a base function like 3 times sinus xx, we get this representation. If we add some more here, we get this representation. If we add some more here, like this one here, we get this one here, and so on and so on. You see that if we use a combination of these 4 different base functions here, 3 sinus x, 1 sinus 3x, 0.8 sinus 5x, and so on and so on. If we use just the combination by just adding all that stuff, we get a very, very complex signal here, obviously, or we can represent very, very complex signals here. And the key idea here now is, first of all, to represent a given time series by a proper or a number of proper base functions, so that this representation that we get through the base functions is more or less the same as the original time series, yeah, which is this one here. So this representation here may be quite good approximation of this one here, yeah, of the original time series. That's the basic idea. Yeah, so Fourier's theorem says that any periodic function can be represented by a sum of sinus and cosine functions of different frequencies. Okay, so DFT, discrete Fourier transformation, originally tries to finds actually a different equivalent representation. So the DFT transformation transforms a time series of length n. Yeah, we start now at time point 0 and go up to time point n minus 1. So the length is again n, into a new representation of n complex numbers with frequencies f, such that this thing holds here. So we have so the new representation of the original representation here is the original representation as at time point t, and also here, and the new representation is a complex number, yeah, at a given frequency f, which corresponds to the corresponding sum of the time slots here, yeah. Each frequency, complex frequency, complex number at a given frequency can be computed. As this one here consists of a real part and an imaginary part, since it's a complex number. Yeah? So the basic idea is to transform the time series x of length n into another sequence of length n, and the sequence now consists of complex numbers, and we call the time slots now frequencies of this new representation here. Yeah? And you see that, yeah, they are basically representations of sinus and cosine functions. Yeah, so the cosine part is the real part, and the sinus part is the imaginary part. And DFT can be interpreted as a transformation of basis vectors, very similar like PCA. So the new basis is spanned by the frequency. So we have the original time series, and we can interpret the time series as of length n as n-dimensional point, and DFT transforms this point into a new n-dimensional space, and the new n-dimensional space is spanned by these frequencies f here that are the corresponding dimensions of this new representation here. Yeah. Well, what does it help? So far nothing, because we transformed an n-dimensional time series into an n-dimensional vector, but we wanted to do dimensionality reduction, so we want to reduce the length. Well, the nice thing of this transformation is that it first of all holds that the Euclidean distance is preserved after the transformation. Yeah? So the Euclidean distance on the original time series in the original time space, so to say, is the same as the Euclidean distance in this new frequency space, which follows from Parseval's theorem. Okay, that's nice, and basically also the linearity of DFT, because the energy of a sequence, which is the sum of the squared amplitudes, is preserved by DFT. That's actually Parseval's theorem, and from that we can infer that the Euclidean distance is also preserved. Okay, still nice, but who cares? Well, the important trick is now based on this observation here. So in practice, the low frequencies, which are the first components, have the highest impact on the representation. Sounds a little bit like eigenvalues and eigenvectors, and that's exactly what it is. But now in terms of frequencies, yeah, because the frequencies somehow represent these cosine and sinus specific things, like those one here. Yeah. So the first frequencies are the most important parts of the representation. This one here. So it contains the most information, very similar to the first principal components if you compute PCA. So focusing on the first C coefficients, first C frequencies in this transformed representation by DFT could be a good choice if we want to reduce dimensionality of a sequence. Yeah? And since the Euclidean distance is preserved, if we use only C components here instead of N, yeah, because the original representation in the frequency spectrum is still n-dimensional, if we only use C out of N, the first C for example, it is even a lower bounding approximation of the Euclidean distance, which sometimes help when it comes down to similarity search and stuff like that. Yeah? And yeah, this approximation will be better when using C DFT components instead of the C original arbitrary timestamps. So a dimensionality reduction to C components in the DFT space is much better than in the original space, because in the original space, if we just take the first C dimensions, meaning the first C time slots, this is absolutely arbitrary. We don't know if we take the time slots that contain the most important information or the least important information. Due to the property of DFT, we know that the first C components are the ones with the highest impact, with the highest load of information. So it is kind of optimal with respect to information loss again. So very, very similar to PCA. Yeah? So bottom line is that DFT has a very, very similar property like PCA. And for the same reasons, we can use just the first C DFT components, the first C frequencies in this transformed feature space as a new reduced feature space.